Hello, welcome to the final one of my video walkthroughs for OCR 21st century. This is for Unit P7. I'm going to go through the June 2014 paper. Just excuse me a moment. I'm going to load up the comments on an iPad next to me so that I can see some of your comments while I'm doing the broadcast. If you do have any questions, please feel free to ask them. However, I may not answer them until the end of the broadcast. Okay, so let's begin with question number 1. The first thing you'll see as you open the exam paper on Friday will be the useful relationship section. These are the equations you'll need. You'll see Earth and the universe, that's P1, sustainable energy, that's P3, explaining motion, P4, electric circuits, P5, P6, and the one that's of interest to us today, observing the universe, which is P7. So you'll see there are about 7 equations there that will be useful to us during the exam. Question number 1 begins with something called the Titus-Bode Law. Now, this isn't in your specification. It's not something you're supposed to know anything about. The exam boards often do things like this and include unknown topics. All the data, all the information that you need to answer this has been provided, in addition to any extra knowledge you might have from P7. So part A says, here, suggest why the Titus-Bode Law was only applied to the 6 planets out to Saturn in the first instance. So what this is, it's an arithmetic sequence that was discovered in the late 1700s, which predicted how far away from the Earth the various planets should be. And question A, why did it only apply to the 6 planets out to Saturn? Well, the reason for that is the other planets hadn't yet been discovered. So only these 6 planets had been discovered at this point. Bode thought that there should be a planet between Mars and Jupiter. Calculate the distance using the Titus-Bode Law. Okay, so the instructions for this are at the top of the screen here. It says we take the sequence of numbers 0, 3, 6, 12, 24, 48, and 96. The numbers are sort of doubling each time. Add 4 to the number, then divide it by 10, and that will predict the distance. So you can see for Mars, they've used 12, and for Jupiter, they've used 48, which would suggest, if this law was applicable, that there should be a number in between. And that number will be 24. So we need to take 24 and add 4 to it, as the instructions tell us, and then divide by 10. This gives us 2.8 as our distance. In 1801, the astronomer Giuseppe Piazzi discovered a new planet, Ceres, at a distance of 2.77 astronomical units from the Sun. Does this support the Titus-Bode Law? Well, given we've just predicted there should be a planet at 2.8, that does agree with the Titus-Bode Law. So again, we don't know anything about Titus-Bode Law. You haven't come into this exam knowing anything about it, but we're just using the data that's been provided and comparing the data. So yes, as the distance is similar to 2.8 astronomical units. Giuseppe Piazzi did not make enough observations to describe the orbit of Ceres. Other astronomers couldn't even find the planet. So why is it important that other astronomers observe the new planet? Well, this is a sort of a how science works question. It's really important that other astronomers observe the new planet because Piazzi could have been wrong. So they need to check the observations in order to increase reliability. Let's see, the table below gives data for other more recently discovered planets. So Uranus, Neptune, and Pluto. Discuss how these results affect confidence in the Titus-Bode law. Well, we can see that for Uranus, it's very similar, 19.6 compared to 19.18. For Neptune, it's fairly similar, 38.8 to 30.06. However, for Pluto, it's way off. Pluto is actually only at 39.44, but the Titus-Bode law suggests it should be around about 77. So we should discuss that. So Uranus and Neptune are quite close to their predicted values. However, Pluto is not close to its prediction. So in order to get all the marks here, you also need to make a comment. So for example, for the 3 marks, you would need to talk about the 3 planets there and make the comparisons. But for the 4th mark, you need to make some kind of conclusion to this. So saying something like the law appears to work best for nearer planets, which sort of makes sense because it's very good up to Uranus. Neptune, it's a substantial chunk off, and Pluto is way off. Most scientists think the Titus-Bode law was just an interesting coincidence. What would be needed to persuade them that the law was not just a correlation? Now, this is the important word here. OCR love questions about correlation and cause, and here they've thrown that word correlation in order to take something from beyond just being a correlation. In order to find a causal link, what is always needed is some sort of scientific mechanism, and this is no different. So a scientific mechanism, all a scientific mechanism means is some sort of explanation involving the actual science rather than just this mathematical relationship here, but an actual science for why this relationship exists. Okay, continuing on to question number 2, which is the first of our 6-mark questions. One of the most distant objects visible to the naked eye is the Andromeda Galaxy. Edwin Hubble first measured the distance to the Andromeda Galaxy using Cepheid variables. He measured the distance as about 1 million light years. They've since adjusted that to about 2.5 million light years. Telescopes have made it possible to make better measurements of parallax and brightness of stars. Now, this is the important bit here. 6-mark question. Explain how using space telescopes gives better measurements of parallax and brightness. So that's one thing we have to do. And explain how this improves the measurement of distance to Cepheid variables. So it's actually looking for 2 quite different pieces of knowledge here, looking for you to assess why space telescopes are better than ground-based telescopes, and also to explain how Cepheid variable stars are used to estimate distance. And we can link the 2 together a little bit as well. So first up, in space, there is no atmosphere. So there is less absorption and refraction of light. In other words, the light can travel unaffected by an atmosphere. It's not going to get bent or absorbed and reduced in brightness as a result. So the light that's traveled across the universe to reach the telescope is not affected by an atmosphere at the end of its journey. So that's the main reason why space telescopes give better measurements of parallax and brightness. As to how we measure Cepheid variable stars, well, we need to say something along the lines of Cepheid variable stars fluctuate in brightness. Their brightness changes. In a very well-defined pattern. Time period for these fluctuations, so how long it is between each peak of brightness, is related to the luminosity of the star. By comparing brightness and luminosity, an estimate can be made the distance to the star. Let's just link these two things together. If less light is being absorbed or refracted, the measurement of brightness will be more precise. And therefore, also the estimate distance. I've had a quick question come through from Max Fader saying, can we have a quick explanation for what a Cepheid variable is and what it does and can be used for? So a Cepheid variable star is a star that's brightness changes. If I do a quick sketch just up here. So this is a graph of time against brightness. Its brightness will go up and down over time. The important thing is when we're looking at stars, we can see the brightness of a star. The brightness is how much light is reaching us here on Earth, how bright it appears to us from where we are in the universe. We don't know how much each star is producing in terms of the power output, the luminosity of the star. However, what's interesting about Cepheid variable stars is that the time period between each of these pulses of brightness is proportional to the luminosity. That time period is proportional to the luminosity, which now allows us to make an estimate of both brightness and luminosity for the star. By comparing the two, that tells us how far away it is. If you think of an analogy here, you could have a 100-watt light bulb 100 meters away from you and a 100-watt light bulb 200 meters away from you. They both have the same luminosity. They're both outputting the same amount of light, but one will appear less bright because it's further away. So by knowing how bright something appears and how luminous it is, and applying some maths to this, you can estimate how far away something is. Okay, let's move on to question number 3. Measurements of the distance to galaxies give a value of the Hubble constant as 71 kilometers per second per megaparsec. Reminder here, a megaparsec is a unit of distance. The mega means a million. So any values of distance where we're talking in millions of parsecs are certainly outside the Milky Way. We're talking about galaxies other than our own extragalactic measurements. Excuse me. So at what distance is a galaxy with a speed of recession of 1800 kilometers per second? Well, let's take a look back at our formula sheet. You'll see there's this formula here. The speed of recession equals the Hubble constant multiplied by the distance. So that's the equation we're going to use. So speed equals Hubble constant times distance. And we want to find the distance, so we'll need to rearrange this equation. So if we divide both sides of the equation by the Hubble constant, we'll end up with distance equals speed divided by the Hubble constant. And we can now plug some values into this. So our speed here is 1800 kilometers per second. And I'm going to write the units in here. Our Hubble constant is 71 kilometers per second per megaparsec. Now, first thing to say here is that the answer to that equation is 25.4. But there is a mark available here for using the correct units for this distance. You can see here that we have kilometers per second on both the top and the bottom of the equation, so we can actually cancel both of those out. And that leaves us with, just on the bottom of the equation, we have per megaparsec. Well, that's the same as having megaparsecs on the top. So our unit here is the MPC, the megaparsec. And that makes sense as well, because we should know from our specification that the megaparsec is one of the it is one of the units used for measuring big distances in space. Lena's asked for a quick explanation of what the Hubble constant is. If you were to plot a graph of speed of recession, so that is how fast the galaxies are moving away from each other, against the distance to each galaxy, what you'll find is that there's a straight line. All the galaxies line up neatly in a straight line here, which tells us that the further away a galaxy is from us, the faster away it is receding from us. And that means that that's evidence then that the universe is expanding, and that perhaps it began with a big bang at the beginning. The gradient of this line is the Hubble constant. And that's a constant that then can be used to, if you know either the speed or the distance to a galaxy, you can use the Hubble constant to predict the other value. Part B, explain why there is a relationship between the distances to far galaxies and their speeds of recession. So this is, as I just discussed there, the fact there is a relationship between them tells us that space itself is expanding. That everything in the universe is moving away from everything else. Space is expanding, so the further away an object is, galaxy is, faster it is receding from us. That would get you both marks here. Part C, scientists can only observe galaxies. They cannot do experiments on the galaxies. They're obviously far too far away. So why are scientists confident that the relationship between speed of recession and distance to far galaxies is correct? Now, again, this is another sort of how science works question. Rather than drawing on your knowledge from the specification, it's your knowledge of an understanding of how the scientific process works. Well, there is a large amount of data. And all of that supports relationship. Also, scientists have come up with a plausible, so a realistic mechanism to explain the relationship. In this case, that would be expanding universe and Big Bang. On to question number 8. Here we have a graph. This is the Hertzsprung-Russell diagram. You should be familiar with this. In particular, you should be aware of the different regions of this graph. It's quite a simplified version of it, actually. But what you should know is that this central path down the middle is the main sequence. That's where stars spend most of their life. That's where our sun is, somewhere along that main sequence at the moment. In the bottom corner here, you'll have the white dwarfs. And then you have the red giants. And above those, up here, the supergiants as well. So as I said, this is quite a simplified version of the diagram, but you may be asked to label all of the parts on this. It does tend to come up in some of these exams. Right, let's have a look at what these axes represent. Well, the horizontal axis, the x-axis here, is temperature. And it wants to know what unit we would put that in. Well, the unit of temperature here is the Kelvin. Although I believe they would have accepted degrees Celsius as well. The vertical axis, we have luminosity. So that is the power output of each star. Part B says one of the axes can also be shown as the colour of a star. So on the Hertzsprung-Russell diagram, label this axis with the colours blue, red, and yellow. Now this is pulling out a bit of science regarding the relationship between temperature and colour. So the hotter a star is, and it's worth noticing at this point that the Hertzsprung-Russell diagram has the x-axis reversed, so the hotter stars are on the left and the cooler stars are on the right. The hotter a star is, the bluer the light will appear. So blue will be at this end of the axis. Red, however, is the cooler of the colours. A cooler star will be red, and in between we will have yellow. And your knowledge of the Hertzsprung-Russell diagram should help you with this. You can see the red giants are at this end of the chart. The main sequence stars, like our sun in the middle somewhere here, is yellow, and then the hotter white dwarfs through to the really hot stars are blue at this end. Now we need to explain this relationship between colours and the number on the axis. So why is it that the hotter temperatures are blue and the cooler temperatures are red? Well, there's 2 points we need to make here. First is that temperature of a star is related to frequency of the light that it emits. In particular, we can add to that the principal frequency. That's the frequency of light that is most emitted by the star. It might emit a whole load of different frequencies, but that's the biggest one. And the other thing that we should bring in here is that frequency is frequency of light. It takes the color of that light. So light with a high frequency will be blue, and light with a low frequency will be red. And the temperature, the hotter the temperature, the higher the frequency. So 40,000 kelvins will produce high frequency blue light, and 2,500 will produce low frequency red light. And on to part C. We need to, part I says, on the Hertzsprung-Russell diagram, put a ring around a star that produces most of its energy by the fusion of hydrogen. Well, we can choose any of the stars on the main sequence. While a star is in its kind of middle age, in its prime, it is on the main sequence here, and that is when it is fusing its hydrogen in order to produce energy. Towards the end of its life cycle, it runs out of hydrogen, and that's what causes it to become a red giant, and then at which point it starts fusing the heavier elements. And then once that's run out, the star will die and become a white dwarf. You should be aware of the life cycles of both small stars and large stars, and in fact, there's a question coming up later in this paper that addresses that, so I'll save that for later. So explain how scientists know that there is hydrogen in stars. Well, this is to do with line spectra. Now, this is one of the hardest, if not the hardest topic in P7. If you would like more detail on line spectra, I suggest you have a look at my YouTube channel. There is a playlist for P7, and in that there is an emission spectra or a line spectra video, which explains how emission and absorption line spectra are formed. It is a tricky concept, but here all we need to say is that they use the spectral lines from the stars. That would be the absorption spectra. Each element produces a unique pattern. Can be compared on Earth to emission spectra. So absorption spectra are what we see when we look at the light from a star through a spectroscope. We'll see most of the spectrum, the whole rainbow, but there will be some distinctive lines, and the position of those lines at certain wavelengths will correspond to the same positions of bright light that you get when you excite certain gases by burning them or passing electricity through them. So it's by comparing the two, you can work out which elements are in the star. Part D, why can black holes not be plotted on the Hertzsprung-Russell diagram? Well, let's have a look back at the Hertzsprung-Russell diagram. Remember, the y-axis here is luminosity. That's the amount of energy that is being given out by the star, whereas a black hole, by definition, does not emit any light. It has a zero luminosity. So would not appear. Question number 5, another 6-mark question. A star's mass is one of the most significant factors affecting the life of the star. Describe and explain how mass affects the life of a star. It's a tricky question, this one, actually. I suspect a lot of students would have been limited to around about 4 marks in this, because they might have included one aspect of this explanation but not the other. And I'll show you what I mean, because there are 2 things the mark scheme was looking for here. The first one is to simply say describe what the properties of a of a high mass star are. So high mass stars are usually hotter and have higher luminosity. That's a nice description there of high mass stars. Big stars, they tend to be hotter and they tend to have higher luminosity. There's other details you can add in there if you want to as well. They tend to have shorter lives and so on. Now, the main thing it's looking for here is looking at the life of a star. It's not just talking about what the star is like, it's looking at the whole life of the star. So there is a difference between the life cycle of a low mass star and the life cycle of a high mass star. Low mass stars become red giants. This is after the main sequence is finished. Once they've run out of hydrogen, they become red giants, followed by nebula and white dwarf. High mass stars, so these are ones that are significantly bigger than our sun, become supergiants, followed by a supernova, and then become either a black hole or a neutron star. And that would get you, I think, most of the marks in this question. You've addressed a difference between high mass stars and low mass stars, as well as describing the life cycles of each one. Part B, a star with a mass of the sun converts around 10 to the minus 5 of its mass to energy in the fusion of hydrogen. The sun's mass is 2 times 10 to the power of 30 kilograms. At this point, I should remind you, you definitely need to take a scientific calculator to your P7 exam, because calculations like this are likely to come up which require standard form and will be tricky if you don't have a scientific calculator. So how much mass is converted to energy during the fusion of hydrogen for this star? So here we know the mass of the sun, and we know what fraction of that will turn to energy. So we need to divide one by the other. So the overall mass is 2 times 10 to the power of 30 kilograms. And we need to divide that by 10 to the power of minus 5. Excuse me, actually, no, we don't. We want to multiply it by 10 to the minus 5. Which is the fraction of the mass to energy, and then that equals 2 times 10 to the power of 25 kilograms. Part 2, the luminosity of the star is about 4.5 times 10 to the power of 26 joules per second. Show that this star converts about 5 times 10 to the power of 9 kilograms to produce this amount of energy every second. Well, the first thing we need to do here is lose this per second business. So let's just say in 1 second, and that means that we can lose the per second there. We're now just talking about 4.5 times 10 to the power of 26 joules, because we're only thinking about 1 second of time. Now, we've got an energy here, we've got a mass, and they've given us the speed of light. This should be a big clue of which equation we need to use. It is on your formula sheet, but it's also the most famous equation in history. It is E equals mc squared the relationship between mass and energy in nuclear fission and nuclear fusion. So we need to rearrange our equation. Let's divide both sides by c squared, and we'll get m equals E divided by c squared. And we can then plug in our values. So 4.5 times 10 to the power of 26 divided by, and you need to be very careful when you're doing this here, use brackets if you need to, 3 times 10 to the power of 8, close the bracket and square it, and that will give you 5 times 10 to the power of 9. It is a show that question. You must show each stage here. You must show how you rearranged E equals mc squared, that you put these values in, and then this will produce the correct answer. There's no mark at all for just saying the right answer here. So just to go back to part I, there's a question in the comments about why we multiplied it. 10 to the minus 5 is a fraction. It's 1/10,000th, I think. Yes, 1/10,000th. No, sorry, 1/100,000th of whatever you're multiplying it by. So 10 to the minus 5 is equal to 1 divided by 100,000. So it's just a fraction. In order to work out what that fraction is of 2 times 10 to the 30, you need to multiply them together, and that will give us 2 times 10 to the 25, which is 100,000 times smaller than 2 times 10 to the 30. Part 3 tells us about a similar star with the same luminosity that fuses 3 times 10 to the 25 kilograms during the main part of its lifetime. Calculate how long the main part of its lifetime is. So it's worth again using units here to help us. If we do 3 times 10 to the power of 25 kilograms, and we divide it, that's the mass that is fused. If we divide that by the rate at which the fusion happens, which is 5 times 10 to the power of 9 kilograms, but this is every second, so kilograms per second, this will now give us an answer. We can cancel the kilograms. It will now give us an answer of 6 times 10 to the 15. Similar to below, we've got per second on the bottom here, so that's like having seconds on the top. So 6 times 10 to the power of 15 seconds is the lifespan. Six A is a ray diagram question. These are very likely to come up because a whole section of P7 is about lenses. Fortunately, these are much easier than they look at first. First thing I would always do with one of these diagrams is look for where, well, let's have a look at it first. So we can see it's one of the more complex type of this diagrams because we've got 2 different sources of light. We've got light from the top of a galaxy and light from the bottom of a galaxy. So we're going to have to do our diagram a couple of times here. First thing I'm going to do though is draw a vertical line through our focal point there. Because our image will be formed somewhere along that line. It won't necessarily be on this dot, and in fact I can tell you it definitely won't be on this dot because that will only happen if the rays are coming straight on. So the image will pass through this dot, but the 2 points that we're considering, the light from the top of the galaxy and the light from the bottom of the galaxy, will not be on this dot. They will be somewhere on this line. The second rule we need to apply is that anything that passes straight through the middle, the exact center of our lens, will continue straight on. So let's begin with our top one here, passing straight through the middle, and we can continue it straight on there. The second rule, and there's 4 marks available for this, so you get a mark for recognizing most of these rules. The second rule is that any other ray of light will go straight on until it gets to the lens, at which point it will be refracted and it will bend and cross over our center ray on this line here, which represents where the image will be formed, the vertical line below this point, this focal point. Now need to do the same for our light from the bottom of the galaxy. So this one passing straight through the center will form an image there, while this one will go straight on until it hits the lens before bending and crossing over here. So this diagram is almost complete. The only thing we should add here is that that's the light from the bottom. This is the light from the top. Obviously, what hasn't been shown here is that actually the galaxy is producing light not just from the top and the bottom, but right the way through. So in between, we're going to have rays of light coming all through, and the result will be an image here of the galaxy being produced, a full image, so which we'll label here as our image. So remember those 2 or 3 rules there. First of all of the images will be formed in a vertical line through the focal point. Any rays that are passing straight through the center of the lens will go in a straight line. Any other rays will be bent by the lens and will meet at and will cross over that first line, the center line, on this line through the focal point. In a telescope, the objective lens has a longer focal length than the eyepiece lens. Explain why. Well, the eyepiece lens magnifies the image. That's the job. Job of the eyepiece lens. The eyepiece lens magnifies the image which has been formed by the objective lens. And we need to refer to the formula that's provided. Again, let's have a look at the useful for relationship sheet here, and we'll see that magnification is equal to the focal length of an objective lens divided by the focal length of an eyepiece lens. So we should refer to that equation. Magnification equals focal length of the objective lens divided by the eyepiece lens. And finally, part C, what are the advantages of using a mirror in place of the objective lens in a telescope? So when we've been considering lenses here, but actually most telescopes use mirrors rather than lenses. There are several advantages. We'll jot a few down here. You only need a couple for the marks in this particular question. First one is that mirrors, don't absorb light, whereas lenses do. Some of the light will be absorbed by the glass in the lens. The other one is that mirrors aren't as heavy so they can be made larger and more easily taken into space. They're easier to make. It's certainly much easier to make a smooth mirror than it is to make a flawless lens. And one of the more important ones is that all frequencies of radiation can be reflected by a mirror, whereas some are absorbed by a lens. For example, ultraviolet light. I get a suntan through a window because ultraviolet light is absorbed by glass, or largely absorbed by glass. On to question number 7, which is the final question in this paper. And it gives us some information about possible sites for a new astronomical observatory. It gives us the height above sea level, the average cloudless nights per year, the percentage of water in the air, so that's the humidity, how far it is from the nearest town, and some further information from an environmental survey. So which site would be the best for an astronomical observatory? By considering each site, explain and justify your choice. So I'm going to refer quite a lot to the mark scheme here. You must consider all of the sites and most of the aspects here with justifications and comparisons, and then make a conclusion. So if I jot down a few of the key things, so site A is the best for cloudless nights. You can see this, it has 360 cloudless nights a year, so almost every night of the year it's good. It's high up, which is helpful for a telescope. It has low humidity. And is far from towns, although there are rare species nearby. It's a bit of a drag, this question, actually, because you do have to go through the motions of summarizing what's in that table. So B, far from town. However, very few cloudless nights. Only 120 all year, so 1 in 3 nights is cloudless, the rest is going to struggle. It's low height and high humidity, so on the face of it, it doesn't look like a particularly good choice for a telescope. Site C is the highest above sea level, 6,000 meters. It's got quite a high number of cloudless nights, not as good as A, but better than B or D. It's low height and high humidity. And finally, D actually we should say as well for C, there are very few living organisms nearby. And D is nearest to town. It's only 30 kilometers away. So that could be convenient if you need to get access from the nearest town. So that's not enough for the answers. That's probably enough. That's not enough for a high level answer here, but what you do need to talk about is why some of these things are good. So height is good because it reduces atmospheric interference. it reduces the chance of clouds and interrupting and so on. Cloudless nights obviously provide more opportunities to observe sky. High humidity is a problem. Because it will increase scattering in the atmosphere. That is, having that moisture in the atmosphere will increase scattering. It'll mean you won't get as clear an image of the light coming from space. Distance from towns. That's a there's two sides of this. Distance from towns is useful to avoid noise pollution, light pollution, but difficult for access purposes. So getting people and resources to the site. And also desirable to minimize environmental impact on wildlife. We want to find the one that has the best one of those. Now, there's no right or wrong answer here. It's about how you've evaluated it, but you should have a conclusion. I'm going to go for site C is the best. It doesn't really matter too much which one you choose, but you've got to justify it. Site C is best because it has low humidity, is very high up, few local organisms, and is near to a town. However, not however, actually. So also, it has many cloudless nights. An answer like that would get you 6 marks. This question, by the way, was aimed at grades up to a C. So summarize what we've done here. We've pulled out the relevant information from the table. We've explained why each aspect of that is useful. And then we've picked a conclusion, and we've justified that conclusion. That's the most important thing, and that should be worth 6 marks. And that's the end of the question paper. So I'm happy to do happy to take some questions now. If anybody wants to add questions to the comments thread, I'll just have a quick read through them to see if I've missed any. Max Feder says, would you say this is the hardest exam of the 3? And also, will the grade boundaries be low due to how hard it is? In my experience, no. I think the P456 content is usually harder for most students. Having said that, it is a difficult paper. Last year, the grade boundaries were higher, much higher than for P456. It was around about 41, 42, I think, for an A star. So I wouldn't expect the grade boundaries to be especially low, but it depends what kind of questions they come up with this year. Vishali has asked, what about the idea that lenses focus different frequencies of light at different points? Yes, I think if that's with reference to advantages of mirrors over lenses, yes, that's that is correct. Because different colors of light are refracted by different amounts, that's due to them slowing down by different amounts when they enter the glass. It is true also that different colors will will be refracted by different amounts when they pass through a lens, so the lens will distort the image. So that's another reason you can put down for why mirrors are better than lenses. Star asks, can I explain retrograde motion? I could give it a go, but actually Brian Cox does a much better job of it. So if you if you Google Brian Cox retrograde motion, there's a video clip from one of his TV series. I think it's on YouTube, in which he does an excellent job of explaining it far better than I can do. Max Fader says, what do we need to know about Hubble telescopes? The Hubble telescope is a particular telescope that was launched in the 90s. You don't need to know anything specifically about that. P7.5, which is the kind of ideas about science part of it, in which you're comparing different types of telescopes, does require you to understand the advantages and disadvantages of space telescopes versus land-based telescopes. So it's worth having a look at that. Layla says, how does the value of the Hubble constant help determine the age of the universe? I'm pretty sure you don't need to know this for P7, but the Hubble constant, if it's in the right units, doing 1 divided by that will give you an estimate for the age of the universe. The reason for that is because it's the rate of expansion of the universe. So in principle, you should be able to work backwards from that to work out how long the universe has been expanding for. Zaid asks, what's the difference in absorption spectra and emission spectra? Again, this is one of the hardest parts to explain. I'd recommend you have a look at. I'm sure there's lots of good videos on this. I've done one that is on my YouTube channel in the P7 playlist for explaining how absorption and emission spectra are formed. Absorption spectra, in summary, would be a full spectrum of light, a full rainbow with dark lines in it. Whereas an emission spectra is the opposite of that. It's like a negative of that. It's a black strip with only the relevant lines picked out. But I recommend you have a look at that video if you want to understand that in more detail. Billy Ball says, does the Hubble use other radiation for images like ultraviolet, etc.? Yes, I think it does. I'm not certain exactly. I don't know a lot about the Hubble telescope, but I think it does use other types of radiation, and certainly there are other telescopes that only use non-visible light. You can learn a lot more about the universe by considering by imaging it with non-visible light, microwaves, radio waves, and so on. Just a reminder as well that if you go to my website, which is cowenphysics.com, the full spec for P7 is there. I haven't made very many videos for P7, but the full spec is there, and any points of the spec that link to a video are linked. Also, I have done a walkthrough question by question of the 2013 paper, which you can access on YouTube. Oh, Max Fader says, can I go over the 3 pressure equations? Yeah, let's have a look at that. So if I just find a blank page. The 3 pressure equations, which I'm not sure, are they given to you on the formula sheet? Let's have a quick look. Yes, they are. Pressure times volume is constant. Pressure over temperature is constant, and volume over temperature is constant. So what this means is that if you increase the pressure, in order to keep a constant value on the right-hand side here, you must decrease the volume. So an example here, if you take a balloon and you squeeze it, you are decreasing the volume. And as a result, the molecules are going to collide with the walls of the balloon more often, so the pressure will increase. because we're dealing with pressure and volume here, we have to assume that two other things are constant here: mass and temperature both remain constant in this one. Similarly, the next one, pressure divided by temperature, is a constant. Here you have to assume that the mass and the volume are fixed, and by increasing the pressure, you will also increase the temperature. And likewise, if you increase the temperature, you increase the pressure. So if you imagine you have a container full of gas and you increase the temperature of that gas, the molecules are going to collide. They're going to travel faster. They're going to collide with the walls of the container more often and with more force. And the result of that will be an increase in pressure. Likewise, pressure, volume and temperature. If pressure and mass are fixed, volume and temperature are directly linked as well. So increasing the temperature of perhaps in a container that's not fixed in shape, like a balloon, if you increase the temperature of the molecules of the gas in that balloon, the molecules will collide with the walls more, and because the balloon can expand, it will, so the volume will get greater. So they're the three gas laws you should be aware of. As you can see, it didn't come up in last year's paper, so there could be a good chance that there would be questions about the gas laws in this year's paper. So just you should be able to apply these calculations. For example, there could be questions which will give you the pressure and temperature of a gas before something is done to it, and then give you the new temperature afterwards, and you have to use the information to find out the pressure. So in order to do that, you would work out the constant, which should stay the same right through the question at the beginning, and then work from the constant and the pressure to work out the new temperature, or whatever the question is. Let me just have a look whether the previous paper, June 2013 paper, it doesn't look like the June 2013 paper covered it either. Well done, Zaid, for being your 300th subscriber. Your prize is an A star. Max Fader, how does a diffraction grating work? You don't have to understand how a diffraction grating works. You do need to be able to explain how a prism works, which is that it refracts light, it bends light. And blue light bends more than red light. That's because blue light slows down more than red light when it enters the glass. As a result, it bends more, so a prism separates out all of the colors into a spectrum. You don't need to explain how a diffraction grating works. You just need to be aware that a diffraction grating can produce a spectrum. So an example question might be, explain how a spectrum is formed by a prism, and you make your explanation. And the next question would be, name something else that can produce a spectrum, and your answer to that would be the diffraction grating. Yeah, Zaid, to confirm it, a star is red, that's low frequency light, therefore a lower temperature than a star that appears blue, because that's high frequency, high energy, higher temperature. Got any more questions? Okay, so this whole video will automatically be put on YouTube once the broadcast is finished, so you can watch back any parts of it that you might have missed. Max Feder says, how do you recommend revising? I would normally recommend a nice long interleaved, spaced out revision. However, given the exam is Friday morning, you need a slightly different approach. I would make sure you've practiced any of the past papers. There are only 2 past papers. There's this one, June 2014, and there's June 2013 from the year before. Although the old specification, I think, was fairly similar. I've never taught it, but I believe it was fairly similar. So you could use those papers. There's also a specimen paper on the OCR website. So make sure you've had a go at all of those papers and you understand your mistakes in them. Also, use the specification. Identify which bits of the spec are just bits of knowledge that you need to memorize. For example, that a diffraction grating can produce a spectrum of light. And another example of that would be how to locate something in the night sky. You would use right ascension and declination. Look through the spec for those kind of things. Pull those out. Those are bits of knowledge that you can try and absorb while kind of doing some last minute cramming, maybe on the night before or the morning before the exam. But yeah, practice the past papers. Get a feel for what kind of style the questions have. I wouldn't worry about the question, why does a diffraction grating waste less light? The answer would be that the glass block would absorb light, whereas a diffraction grating wouldn't. But I wouldn't. I think that's outside of your specification. I wouldn't like to guess on the topics that could come up for the 6-mark questions. You can usually, there's certain topics which are too limited to come up, that could only be 1 or 2 word answers, but there have been a whole range of different ones that have come up in the past. Eclipses came up 2 years ago, and you can see a few in this one. In fact, as Darth Grizzly says, the Shapley and Curtis argument, the Curtis-Shapley debate, that actually did come up in June 2013, I believe, in a 6-mark question. And as I say, there is a video for every question in 2013 on my YouTube channel, so you can take a look at those. I'm sorry, the 2014 P7 paper I can't provide to you because it's not published by OCR yet, but your teacher will have access, so please ask them, or if you're at my school, drop me an email and I'll provide it to you. List of formulas on the front page, yeah. In fact, the page we're looking at right now, that is the formula page for P7. They provide you with all the formulae for P1 to 6 first, and then you come on to P7. Lens power and magnification, obviously related to lenses. Speed of recession, Hubble constant times distance. That's to do with the expansion of the universe. You've got your 3 gas laws: pressure, temperature, and volume. And then energy equals mass times speed of light in a vacuum squared, or to put it in the more commonly known way, E equals mc squared. Okay, I'm happy to take some more questions, but if there aren't any, I'm happy to wrap it up. Yeah, Daniel Butcher, the video will be on YouTube as soon as I've finished the broadcast. Yeah, I would give it a few minutes, I think, but it will appear at the top of my videos list. No, I'm afraid I'm not going to be able to do another stream tomorrow, which is why I've done it this evening rather than the night before the exam, because I'm not available tomorrow to do that. Yeah, those of you at Preston Manor, there's going to be a revision opportunity, revision lesson tomorrow, period 2. Okay, thanks everybody for tuning in. I hope you found it useful. If you do have any more questions, feel free to tweet me or add comments to this video or whatever you want to do. Don't forget, the whole spec is on cowenphysics.com with links to specific videos. Also on the YouTube channel here, you'll find a few videos related to P7 topics, as well as walkthroughs, question by question, of the whole of the June 2013 paper. This video of the June 2014 paper will be online as soon as YouTube have processed it, once I've finished the broadcast. So thank you very much, everybody, for tuning in, and really the best of luck in your exam. I think for every student, it's pretty much the last exam. So well done. You deserve a good rest on Friday afternoon, but don't give up yet. You've got to push through. Don't leave anything in the tank. Bye.